Numbers are thrown out all the time.
Are they proof of some truth or just fluff that bluffs us? These statistics need some serious looking into. I'm Brendan Fernandez, and that's what I'll do. Because some numbers are just worth figuring out. June 21st, 2013, 12 noon. The haze surrounding Singapore turns impenetrable. The readings? PSI at 401. Air pollution is now hazardous. But what do the numbers mean exactly? More critically, what is going into our lungs, our hearts, our bodies with every breath we take?
The new Satay Club. Famous for satay, of course, but also barbecued favorites of all descriptions. There's something about a charcoal fire that makes everything taste good. The smoke from the open coals perfuming the food, carrying delicious cooking smells to every table in the area. However, not too long ago, al fresco dining establishments like this one would have been empty, deserted, abandoned, because they were all smoky for the wrong reasons.
When a smell of burning hangs in the air and visibility drops, we know it's that time of year again. For years now, forest fires raging in Indonesia have been causing the haze in Singapore. Air quality is horrible. To find out just how horrible, Singapore relies on the PSI scale. The PSI stands for the Pollutant Standards Index. This is an index developed by the US Environmental Protection Agency.
PSI is basically derived using 5 components, mainly sulfur dioxide, nitrogen dioxide, ozone, carbon monoxide, and PM10. PM is basically a particulate matter, so it's simply known as particles. So PM10 basically particles smaller in size of 10 microns.
Just how big is a 10 micron particle? 1 micron measures 0.001 millimeters. What about 10 microns? If you took a human hair and split it widthwise into 7 equal parts, each 1/7 of a hair's width would be 10 microns wide.
Sulfur dioxide, nitrogen dioxide, ozone, carbon monoxide, and PM10. These 5 pollutants are what make up the PSI reading.
And how does it affect us? Let's break it down. First, sulfur dioxide. Smells like burned matches. Exposure for as little as 5 minutes can cause problems. Effects of exposure: eye irritation, feelings of tightness in the chest, and a worsening of any breathing or heart problems. Next, nitrogen dioxide, commonly found in vehicle emissions. So if you live near an expressway, it's likely that your exposure to nitrogen dioxide is higher.
Healthy people could be affected with airway inflammation. People with asthma, children, or the elderly could come down with more breathing difficulties.
Ozone. It's good when it's high up in the atmosphere, but bad for us when it's at ground level. Ozone levels can increase especially on hot, sunny days.
Ozone worsens existing breathing problems and reduces lung function. Children are especially susceptible because their lungs are not fully developed yet.
Carbon monoxide, emitted whenever burning occurs. When inhaled, carbon monoxide inhibits the supply of oxygen to the heart, the brain, and other organs and tissues. Finally, PM, particulate matter.
PM10 is measured in micrograms per cubic meter.
How small is that? 1 million micrograms make up 1 gram.
When you are exposed to PM10, you get stingy eyes, you get irritation to the eyes, you get irritation to the nose, you get a runny nose, you get a sore throat. Okay? Sometimes when it's really bad, you get wheezing, you get difficulty breathing. But what's actually more dangerous than PM10 is actually the PM2.5, which refers to the particle size of 2.5 microns.
PM2.5 particles are 4 times smaller than PM10 ones.
The difficulty with PM2.5 is that it doesn't get filtered out by the defenses in the upper airway, the nose, the throat, all the cilia and the little wavy things in the airway, which helps to filter out the dust. It bypasses all our body's natural defenses and lodges into the lungs. And there's also a risk that the particles of 2.5 microns may actually be able to get into the bloodstream, because there is evidence to suggest that when people are exposed to PM2.5, there's a higher risk of heart attacks and of sudden death.
PM10 and PM2.5 are present in such high concentrations because of the fuel source of the haze. We know the haze is caused by fires in Indonesia, but what's actually burning? The Indonesian forest fires are unusual because they are fueled by peat.
Peat behaves like low-grade coal. It burns dirty, which means it burns with a lot of unhealthy emissions. And in the Indonesian forest, the peat is quite often found in damp conditions. So if you were to sprinkle water on burning charcoal, you would quite literally have the effect of putting smoke in your eyes.
These fires are very hard to put out. The peat is pretty thick below the ground. It goes up to 4 kilometers.
4 kilometers?
4 kilometers,
okay,
beneath the surface. And then once it catches, it continues to smolder, for a long period of time. And it could burn even under low moisture conditions, and very different from other fuels.
It's this smoldering effect which makes peat fires unique and uniquely harmful. So what is the effect of all the pollutants we are breathing in? PSI 100, unhealthy air quality. The effect? Being in air that is at PSI 100 for an entire day is like smoking 1/6 of a cigarette. So at PSI 300, hazardous air quality, every person exposed for an entire day would be smoking the equivalent of half a cigarette. Doesn't sound like much. But multiply the effect by 5.3 million people over weeks of exposure, and think of forcing children and those already suffering with respiratory issues to smoke. You get the idea. To know about the amounts of pollutants we're taking in on any given day, we refer to the PSI. But how exactly is it derived? Is it an exact science that tells us when the air has turned from healthy to hazardous? The haze hazard is a burning issue. It's a threat we can smell. But how do we know what is in the air we breathe? For that, we need an air monitoring station.
In Singapore, there are 14 air monitoring stations all over the island. They're placed in the north, south, east, west, and central parts of Singapore. Everywhere.
These locations are chosen because the air around them is pretty much the kind of air ordinary Singaporeans are exposed to.
So this is an air monitoring station. How is PM10 measured? Air comes into the top there. It then passes to this contraption, which is a heater that heats the air to 8 degrees Celsius or higher than the surrounding air, which reduces the moisture. Air passes through to here, where the particles in the air are collected on a filter tape. The filter tape is then irradiated with a beta ray. The readings are then sent to the main data management center at the National Environment Agency.
The monitoring stations around Singapore are constantly sampling and analyzing 5 key air pollutants: sulfur dioxide, nitrogen oxide, ozone, carbon monoxide and PM10.
This is the air monitoring station. Air comes in through here, and these four machines, called analyzers, check it for pollutants. Carbon monoxide, ozone, nitrogen oxide, and sulfur dioxide. Now these are 4 of the 5 components that go into the PSI reading.
Pollutants in the air are measured in tiny amounts called micrograms. But of course, we don't hear about micrograms of pollutants in the news. We're given the PSI reading. PSI is not a composite index. That means that we don't get the numbers by adding things up. So it's not a matter of, for example, adding levels of carbon monoxide to sulfur dioxide. Instead, we do this. First, we focus on one pollutant, the pollutant with the highest concentration in the surrounding air. So in a haze situation like we have in Singapore, particulate matter, or PM, is the pollutant most concentrated in the air. So we look at the amount of PM measured.
Imagine over a 24-hour period, 430 micrograms per cubic meter of particulate matter, or PM, was measured. What does that mean? Is this high or is it low? So how do we use this number to figure out the PSI reading?
430 is here, within the range of 425 to 504 micrograms per cubic meter. How high is that on the PSI scale? By referring to this table, we can see that the PSI falls between 301 and 400.
430 falls between 425 and 504 on the PSI table. So let's take 430 minus 425, which gives us 5. Then you take 504, the higher number in the range, minus 425, which gives you 79. Now we have to divide this number by this number. Now this is where it gets complicated. These numbers we got from the PM reading we had earlier. If you look at that table and go across the row to the PSI column, you'll see that this reading corresponds to a PSI value of 300 to 400. That's why these numbers are here. Now, once we figure out what X is, we'll know what the PSI value for the day is. X gives us the PSI reading for that particular day. Now this looks complicated, it's because it is. I needed some help to figure this out. But X works out to about 307. If you look at where 307 is on the PSI reading table, that's in the hazardous range.
To allay the fears in the public, we need to establish a tipping point, because right now the general public are unaware about what is really a tipping point. Is it going to be 401? Is it going to be 500, which is the maximum limit of a PSI standard? The PSI standard can only range from 0 to 500. Is 500 going to be established as a tipping point, or is it going to be 450 or something lower? So this has to be established to have a clear strategic plan to combat haze.
You know, I don't remember the haze being a problem when I was a kid, so I thought the haze in Singapore was a recent development. But when we did some research, we found something surprising. Our haze problem is older than I am. 10th October 1972, 5 p.m., more than 40 years ago. Visibility at Changi Airport was down to just 1 kilometer, a huge drop from the usual 20 to 30 kilometers.
3 days later, the whole island was affected. Even in the day, motorists were driving with their headlights on along Orchard Road and Nicole Highway.
People began complaining about the white smoke that was choking them and irritating their eyes.
Satellite images showed raging fires in Sumatra and Kalimantan.
3 years later, in 1975, it was a reddish haze that got the public worried.
This unusual haze hung over the eastern and southern parts of Singapore, giving the sun an unfamiliar orange hue. This time, the haze was coming from jungle clearing in Johor Bahru and Kota Tinggi in Malaysia.
1977. Haze shrouded the entire island and was as high up as 366 meters. Also, a housewife in Ghim Moh reported seeing hailstones falling from the sky. So the recent ice storm in 2013 wasn't the first in Singapore's history.
Over the years, the pattern became familiar. But back then, there was no PSI or any other indices used to describe the air quality.
When eye irritation was a problem for a lot of people in the 1982 haze, the government revealed that fine particles in the air had reached a concentration of 300 micrograms per cubic meter.
In today's terms, that would place the air quality at PSI 192.
In 1997, while Singapore was in the grip of the Asian financial crisis, things got even gloomier. The haze came back with a vengeance.
The highest PSI over a 3-hour period, a record of 226. This was the first time air quality went over PSI 200 into the very unhealthy level.
After that, on September 26th, a plane crashed in Medan, Indonesia, killing all 234 passengers on board.
Later, 2 ships collided in the Straits of Malacca. Only 5 out of 34 sailors survived. Poor visibility because of a thick haze was blamed for both accidents. In Singapore, about 81,000 people needed medical treatment for haze-related ailments. Medical bills? $2.2 million.
If you add up the losses to the tourism industry, the healthcare costs, and the loss of productivity due to absence from work, the total cost to Singapore was $319 million, at least. Total cost to the region, $9 billion US. After 1997, we had a few good years.
PSI did hit 150 in 2006 and 108 in 2010. Those are unhealthy levels, but overall, it felt like the worst was behind us. And then the haze came back.
The last 6 years were good ones for clean, green Singapore. The haze was an annoyance, but it was bearable. Then came June 2013.
The severity of the haze this year caught us all by surprise. But the thing is, we know that the dry season in the western part of Indonesia runs from May to October. We know that slash and burn techniques are used to clear land for agriculture. So why didn't we see the problem coming? First, we need to understand how haze is predicted.
This is Tracy. She's going to help.
First, the number of hotspots and their distance from Singapore.
In this particular year, for some strange reasons, and the month of June happened to be drier than usual, and the peat fires occurred in the Riau province at locations that are not too far from Singapore.
Next, how many particles and which gases are given out. Indonesian forest fires tend to be peat fires. They smolder and they burn dirtier than other forest fires. Bigger particles fall out of the air quickly, but finer particles like PM10 and PM2.5 travel a lot further. Next, atmospheric pressure. The further away we get from ground level, the lower the atmospheric pressure. So, when pollutants rise higher, they encounter less air pressure. They scatter and mix freely with the air, becoming a toxic cloud. Where does this toxic mixture go? That depends on wind strength and wind direction. Finally, the time of day. During the night and early morning, air tends to be stagnant. Pollutants are held closer to the ground. The haze may seem thicker at these times. At mid to late afternoon, however, pollutants scatter more freely, become less concentrated, and the haze seems thinner.
Okay, so that's what we need to know in order to estimate where the haze will go and how bad it will be. But why do we sometimes get it wrong?
Unfortunately, each of the parameters that are being fed into the mathematical model designed to predict about the haze has its own uncertainty. So one would be the intensity of fires and the rate of emissions of chemical pollutants. Unfortunately, at this point in time, we don't have a firm handle on being able to quantify as to what kind of chemical pollutants would be emitted from peat fires and with what rate, meaning with what speed they will be emitted into the air. On top of that, we also want to locate the hotspots, and we also want to count the number of hotspots. So although that could easily be accomplished with the use of remote sensing tools, for example satellite images, however, the thick clouds that we have sometimes tend to obscure the satellite images, and therefore we happen to underpredict as to how many hotspots we have.
The air is good today. Let's hope it stays that way. But we can't rely on the wind always being in our favor. We can do more. Prepare for the worst case scenario. Protect the most vulnerable. And make information readily available so when people need to act, they know what to do.